Testing, testing. Okay. Testing 1, 2, 3. Testing 1, 2, 3. Okay, the delay is extremely big. The delay is at least 30 seconds long from the time I speak to the time when it comes up on stream, because I have it on the other device next to me and I can see. So yeah, if you have any questions, it probably be a little bit of time before I actually reply to them. Anyway, welcome to our SMO Open review for the solutions. Okay, what are my feelings for this particular competition? It's a very mixed feeling. I don't know how to describe it. In a sense, I feel that the questions are straying a little bit too far away from math and pit. But in a sense, I also think, okay, maybe the questions they have some relevance, right? They encourage you to think creativity. Um, so a little bit of both. Anyway, some of these questions are quite simple, but at some point in the middle of the worksheet, suddenly the question changes to become quite difficult. That's my feeling of the paper. Anyway, let me start to go through the worksheet now. Okay, question number 1. So question number 1, what we have is this. A is the limit of the summation for n, r equals n all the way until 2n on top of r squared, and then from r equals 1 to n of r squared below. So basically A is going to be the value of n squared, n plus 1 squared, n plus 2 squared, all the way up to 2n squared. And denominator, we have 1 squared plus 2 squared plus all the way up to n squared. Now, actually that's not exactly A, because A is the limit, right? But rather, let's call it our expression. So our denominator here, obviously we have a formula for this. It will be equals to n times n plus 1 times 2n plus 1 over 6. And then the numerator here, what we can think of it is that we can think of it as a difference of two sequences. I can think of it as I take everything from 1 squared all the way up to 2n squared. But then now I'm going to remove the first few square numbers all the way up to n minus 1 squared. So if you think of it that way, then you realize, oh, okay, I need to apply the formula twice. The first one will give you 2n, 2n plus 1, 4n plus 1 over 6. That's from here. And then we also need to apply it to the part behind, so there will be a minus away of n minus 1, n, and then 2n minus 1 over 6. Okay, so when we do simplify the fraction, you can see that this is going to be basically some cubic here minus some cubic as well, right? Divided by some cubic. Okay, and now here's the idea. The idea is that when n actually goes towards infinity, the things that matter are no longer the smaller terms. Only the big terms matter. So when n goes towards infinity, you can see that actually we can get the value a now. Actually, I claim it is just going to be, wait, I just realized I didn't write this fully. A is just going to be this. 2n times 2n times 4n minus away n times 2n over n times 2n, which is going to be, if you look at the expression, 16 minus 2 over 2, which is 7. Now, as for why n is this expression, why a is this expression, where we just ignore all the terms that are not as big, you can see when n goes towards infinity, n cubed is a lot bigger than n squared. So you can put, for example, like double arrow to make it say a lot bigger. Same thing is a lot bigger than n, same thing is a lot bigger than 1. So basically, you can just ignore the smaller terms. Okay, so this is a common idea using limits. When you study limits in the future, you'll see this idea as well. Okay, so with that, we have the final answer of 7. Okay. Continuing on. Question number 2. The solution of this inequality. The solution of this inequality is a less than x less than b. Find the value of a squared plus b squared, round down. So when we have this kind of absolute value less than another absolute value, One idea is to split cases, right? And consider, okay, whether the first value C is less than D, whether negative C is less than D, C less than negative D, right? Or negative C less than negative D. But instead of splitting so many cases, it's a lot easier for us to just do one. For us just to ignore the absolute value by taking the squares. If I square the left hand side, this is the expression I'm going to get, right? If I square the right hand side, this is the expression that I'm going to get. And then the left hand side squared must be less than the right hand side squared. This is a fact. Okay. And now what we have from here is that we have the fact that okay, we can just use difference of squares, move over. Right? 0 is less than difference of squares on the right hand side. Right? This squared minus away this squared. And if you do the calculation, you end up with, so the x squared minus 4x plus 3. Okay, first let's do the plus. The sum of those two terms is equals to what? The sum of those two terms will be 2x squared plus x squared, so it's a 3x squared, minus 3x minus 4x, so it's a minus 7x, plus 2 plus 3, so it's a plus 5. Then the other one is a difference. X squared minus 2x squared is negative x squared. Negative 4x minus negative 3x is positive, no, it's a negative x as well. And finally 3 minus 2 is a 1. Okay, so this is what we get. Okay, so here we have two things multiplied to give you 0, and actually one of them you already know how to deal with it, which is the first one. Because the first one is always positive. If you take a look at this first one, if you take a look at the discriminant, which is the b squared minus 4ac term, you can see that it will be 7 squared minus 4 times 3 times 5. This is less than 0. And if it's less than 0, it tells you that, okay, this is always positive. Okay, it's always positive because if you think of the quadratic, it will always lie above the x-axis. Right? So for example, this is your x-axis. Then you can have the graph of y equals to this thing lying above, right? No solutions. Okay, so we don't have to deal with the first guy. The first guy is always going to be positive, so we just need to deal with the second guy. It tells you that the second guy is always positive as well. So that means the resulting answer is actually just the solution of this. Now, of course, I can go and use the quadratic formula, figure out the two x-intercepts to figure out the solution set, right? But here we don't have to. If you can recognize that basically by drawing the graph out, I want this thing here. We can recognize that A is a solution, B is a solution. So how do I find A and B? We don't have to. We can just use Vitas formula, right? So by Vitas, we know that in fact, the value of A plus B is equals to the sum of roots, which is negative of this guy divided by this guy. And A times B is the product of roots, which is this guy divided by this guy. So from here, we can figure out A squared plus B squared will be equals to A plus B squared minus 2AB. Okay. Oh, sorry. So this is 3. That is the final answer. Okay. Continuing on. Next one, question number 3. Find the floor of B where B is this guy. So when I see a summation that looks like this, immediately I'm thinking, okay, can there be some kind of a telescoping series? Can we express this as a difference of two terms so that when I add them up, it's a lot easier to do so? Now, it's not so obvious, right? Because of the fact that there's a power of 2 on top. But if I'm looking for anything that may be slightly familiar, then you might recognize, okay, this looks slightly familiar. The denominator here looks slightly familiar because of the fact that we have 1 over k plus 1 times k plus 2. We know that this can be written as 1 over k plus 1 minus 1 over k plus 2, right? So therefore, this whole thing can be written as, okay, maybe not the whole thing. Maybe let's just focus on each individual term. So each term can be written as k times 2 to the power k over k plus 1. In fact, I'm going to bring the 2 to the power k downwards. Okay. And then I also have a k over k plus 2 to the power k. Right. It's a minus in between. Huh? Now, what do you notice? Well, this fraction is very close to 1. This fraction is also very close to 1. I can write it as 1 minus 1 over k plus 1 to the power of k. Subtract away a 1 minus 2 over k plus 2 to the power of k. Right. So then you should notice, okay, the 1 times 2 to the power of k and the 1 times 2 to the power of k, they disappear. In the end, the terms I'm left with are exactly 2 over 2, 2 over k plus 2 times 2 to the power of k, right? And minus 1 over k plus 1 to the power of k. And so I can combine it together. I can write the first one as 2 to the power k plus 1 over k plus 2. And then the second one as 2 to the power k over k plus 1. And when I see this, I'm very happy. Because these two things, they look like each other. Right? These two things, they look like each other except that I replace k over here by k plus 1. Right? K I replace by k plus 1. And if I replace k by k plus 1, then k plus 1 gets replaced by k plus 2. So this guy and this guy are basically just the same terms, except that the numbering is different. So with this, I'm very happy. And now I can go on and proceed to find the sum. So the sum is, we start from k equals to 1. That will be 2 squared over 3 minus 2 to the power 1 over 2. And then when k equals to 2, it will be 2 cubed minus over 4 minus 2 squared over 3. And when k equals to 3, it will be 2 to the power 4 over 5 minus away 2 cubed over 4. So on and so forth until k equals to 10. And that is the last term. 2 to the power 11 over 12 minus 2 to the power of 10 over 11. So let's do our favorite thing. So cancel, 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 and so on and so forth. The things that I am left with over with are this term and this term. So they are, this is 2 to the power 9 divided by 3, right? Which is 512 over 3. This is just 2. Oh, sorry, this is 1, in fact. So this, in the end, when you calculate out, will be 169 and 2 over 3. Okay. So when you round down, the value is 169. Okay, question number 4. Random school math question, or maybe JC math question, inside this SMO. Personally, I'm not a big fan of it, but I understand that because SMO, they say they want to gear towards closing the gap to school syllabus, I can understand why they put it inside, although I'm not happy about it. But anyway, how to do this? There's two ways to do this. If you know integration by parts, you can do this by the idea. Right? Because of the fact that, why do we know integration by parts? Well, integrate this guy, we don't know the expression. But we do know what happens when we integrate 1 over square root of 1 minus x squared dx. This is just a sine inverse. And this looks like the expression we have here. So our aim is to get somehow from here to here, and integration by parts will provide that idea. So integration by parts is basically integral of u dv equals to uv minus integral of v du. So the way I remember it is, I remember it as, okay, I integrate v and then I differentiate u. And I put the integral sign here. So here, where's the u dv here? Well, actually it's going to be 1 times this. And this is the dv part. So integration by parts tells you, if I integrate square root of 1 minus x squared, I'm going to think of it as 1 times this. So first I'm going to integrate the 1 to get x times 1 minus x squared. And then I'm going to, oh wait, I think I might have remembered wrongly. I think I might remember wrongly. Wait, is that integral sine inverse x? I think I might have remembered it wrongly. If you differentiate sine inverse, you get 1 over square root of 1 minus x squared. But how come I have an x here? Let me see. Yeah, how come I have an x here? Yeah, something is wrong somewhere then. Huh. Or maybe it is not possible to do by integration by parts. But it should be though. I wonder what's the wrong working here. Differentiate. Oh, okay, I understand why already. Because when I differentiate this term, I generate a second copy of x on top. Yeah, so that's the problem with this. Okay, how do I patch this issue then? Okay, so I have to throw out my integrating by parts idea because just now when I was working on it, I was sure that it worked. I didn't check through the details of it. So now that I'm actually looking at it, I don't think integration by parts work. Yeah, so unfortunately, I'm going to throw this idea out of the window. Sorry about it. Okay, so this is gone. But anyway, I mentioned I had a second idea, so I'm going to use that second idea here. Um, the second idea is actually the idea I had at first, before I started considering integration by parts. My first idea instinctively is to do a trigonometric substitution, which is to do let x be equals to sine of theta. Okay, now how does this change the question? If I have integral of 1 minus x squared, basically what I'm saying is that this thing here I can change to integral of cosine theta, right? Because this guy simplifies to cosine. But of course, if x is sine theta, then dx will be cosine theta d theta. So because of that, I need to multiply by another copy of this. So actually, this is integral of cosine squared theta d theta. Okay. And then what I can do is that I can use the double angle formula. I can write this as integral of 1 plus cosine 2 theta over 2 and then integrate it. So integrate the half will give you half theta. Integrate this, it will give you sine 2 theta over 4. Of course, usually people put a plus c, but here we don't really care. Now, how to express this back in terms of x? Well, if x is sine theta, then the relationship between theta and x can be drawn out by a right angle triangle. For sine theta cosine theta over 2 once you apply the double angle formula. And then you can get cosine theta from the diagram as well, right? Because of the fact that the bottom one is this when you apply Pythagoras theorem. So then the other expression will be equals to half of sine theta, which is x, and then cosine theta, which is square root of 1 minus x squared. So because of this term, that's why I was thinking of integration by parts actually. But probably I made some mistake there. Because integration by parts doesn't give me the half in front, right? So that is the problem. Anyway, so once I've gotten this already, now I'm happy. Okay, what I just need to do, I need to look at the boundaries. Okay, so I look at the boundaries from 0 to 1 over 3. Obviously, when you have 0, this is 0, this is 0. So that's very nice, right? And 1 over 3 will just give you half sine inverse of 1 over 3, right? Plus half of 1 over 3 and then square root of 1 minus 1 over 3 squared. So then this part behind here has to be the value of b, the one that's given in the question, the one that's here. Okay. So then once you go calculate out, we can see that here b will be equals to 1 over 6 times the square root of 8 over 9. When you simplify it, it will be equals to square root 2 over 9. And that means that b squared will be equals to 2 over 81. And so 1 over b squared round down is exactly 40 because it is 81 over 2 rounded down. Yeah, so this is the idea. Okay. Continuing on, question number 5. Random vector question. For any two vectors A and B in a Cartesian plane, it's known that A plus lambda of B, the modulus, right, which is the magnitude, length of it, is always at least the length of A for all real numbers lambda. Find the largest possible value of the scalar product A dot B. Now for this one, you should just depend on your intuition. If you have the correct intuition for this question, your intuition should immediately shout that the value is 0. Because you can choose any value for lambda. So you basically take a vector, you add any copy of a vector, any multiple of a vector to it. There's probably bound to be something that is shorter than this, right? In most scenarios. So let's discuss that. Let's say this is A. Let's say this is B. Where is lambda of B? Well, if this is B over here, then I can demonstrate lambda of B by actually looking at this line over here. Okay. This line over here is the lambda of B, because any vector along here is basically a multiple times of B, right? So A plus lambda of B actually represents what? Actually represents basically all the resulting combinations of these two vectors. So it could be that, for example, I go here, I go B first, right, and then I go here. Okay, I could be I go here, then go here. I could be go here and then go here, and so on so forth. Sorry. If I add, in that case, it will be go where? If I add here, it will be like that, right? But already you can see some examples. If I do a little bit like this and I add here, this length probably is going to be shorter than this length if it's not a right angle. So if A is not orthogonal, which is perpendicular, if A is not orthogonal to B, there exists some lambda B, right, plus A is going to be shorter than the magnitude of A. Finish. So therefore, A should be orthogonal to B. The dot product is supposed to be 0. Now, this idea is a more of an intuition-based idea. But of course, if you don't want this intuition-based idea, you can go for a more algebraic approach. For a more algebraic approach, what you can do is you can start from this inequality. We can actually try to square it. If we try to square it, we can get that, actually it's A plus lambda B squared at least A squared. Now, what does it mean by square? Actually, you don't really mean square. This, if you write this notation, technically you're wrong, because there's no such thing as a square of a vector. What you have when you have a square actually is the dot product. So that means when dot product, this thing here with this thing, it has to be at least the dot product of A and A. So if you rewrite that equation, then what you can see is that, okay, you have this thing here, right, times this thing, which happens on both sides. So later we can cancel this guy out, right? Then there's a lambda A dot B, there's a lambda B dot A, but these two guys are going to be the same. And then there's a lambda squared dot, lambda squared B dot B, like that, right? Okay, so cancel out on both sides, this guy and this guy. What you get that this guy here is at least 0. Yeah, this guy here is at least 0. Now, if this guy here is at least 0, we can ask what happens if this is not 0? If this is not 0, what happens is that you can choose the value of lambda, right? And you can choose, for example, the B vector to be the very close to 0 vector, right? Actually, no, sorry, the B vector is fixed. Right? So actually, what does this mean that the dot product must be at least 0. Hmm. Okay, okay. You can treat it as a quadratic in terms of lambda, I guess. So you can treat it as a quadratic in terms of lambda. You have basically a magnitude of this b squared times lambda squared. Right? And then you have plus 2 this, whatever this is, right, times lambda is at least 0. And for this quadratic to be true, this guy here must be at least 0. Otherwise, there will be some situation where the quadratic can be less than 0. Because the b squared minus 4ac term will be less than 0, right? When the b squared minus 4ac term is less than 0, you know that there's some value where it is uh, less than 0 as well. Okay, so that's the more algebraic approach. But the thing I'm hoping more of you can see is the intuitive idea. If you have the intuitive idea, you don't need to do the algebraic idea for this question. Okay, next one, question number 6. Suppose we have these two quadratic equations with a common root w, find the value of 7w squared minus w cubed. This question is a little bit funny, right? Because actually, if you start on the right path, it's very short, but you may not start on the right path. Since they have a common root w, let's put that in. So we have that w squared minus mw minus 36 is 0. And then w squared minus 6w minus m is equals to 0. This is what we have. So what can we do here? Well, some of you might be thinking of eliminating the w squared, but personally, I'm more interested in eliminating the m because I noticed that there's no m here. So to do that, we multiply the second equation by w. And then now I can subtract with the first equation, right? But once you subtract, something very interesting happens. Once you subtract them, you can see that you just get w cubed minus 7w squared plus 36 is 0. Okay? So then, wait, something is wrong. I use this minus this, right? Wait, what? Wait, let me check my working again. I use this to minus this. Oh, correct, correct. Because the expression y1 is the negative, right? So you just need to bring this guy over to the right hand side. You can see that basically 36 is equals to 7w squared minus w cubed. Okay. Okay, question number 7. This is already a very weird question. So I'll present two different ideas. And idea number 1 only exists because I already know how to do idea number 2, even though idea number 1 is the cleaner method. So idea number 1 is this very funny looking expression that seemingly come out of nowhere. In fact, AB plus 2AC plus 3BC is at most 3 over 4 of A plus B plus C squared. Seems like come out of nowhere, right? Now, why is this true? Because this thing here, if you expand out, what you can see is that, okay, if you expand out, you can cancel how many? You can cancel, let me check. Okay, then let me multiply by 4 first, so that it's a bit easier. So if you have 4, then you have 4, 8, 12, 3a squared, 3b squared, 3c squared, right? 3a, no, not 3b, 6ab, 6bc, 6ca. Okay. So this is the same thing as saying you have 2ac and then 6bc is at most 3a squared, 3b squared, 3c squared, and then plus what? Let me see. There's 2ab left over, there is okay, that's it actually. Now why is this true? Why is this true? Well, here you notice that there's two terms involving C, right? So our C term is spread pretty thin. And in fact, if you use, let's say, 3b squared and 3c squared, it just nice directly can complete the square of this 6bc. So if you combine this together, that is going to be a 3 times of b minus c squared. What about the remaining terms? There's still some kind of c, right? Okay, but the remaining terms, it looks like this. 3a squared plus 2ab, and then there's a 2ac. We can actually recombine it on the right side as 3a squared, 2a of b minus c. Then you just have an equation in terms of b minus c and a. So if I consider, for example, a general quadratic equation 3x squared plus 3y squared plus 2xy, I think it's very easy to see that this is always at least 0. Right? Okay, so therefore this is true. But what that gives you is that this is at most the value of 3 over 4 times 100 squared, which is equals to 7,500. Now, if you feel that this is an extremely weird idea, you should feel this idea is extremely unnatural. Because when do we even think of coming up with this number 3 over 4? That's where actually idea 2 comes into play. So idea 2 was the idea that I used this question. And then idea number 1 is the idea I only discovered once I finished the question already. So in your thinking process, you should basically never use idea number 1, even though it's good for solution presentation. Idea number 2 is more of a smoothing type idea. So smoothing type idea is the idea of adjusting variables so that behaves a bit nicer. The simplest example is that, okay, if, for example, if a plus b is equals to 10, right? Find max a times b. Now, of course, you can use AMGM here, but the idea is that, okay, if a is at this value and b is at this value, I can bring them both closer to each other, and then the a times b value will increase. Same thing here. You can see in this question, I think it's a pretty straightforward, that the ideal case, the best case, the best case is when C is the largest followed by B followed by A. How come? Well, because the coefficients with the biggest products are the ones with C, followed by the ones with B, 3 and 1, followed by the ones with A, 1 and 2. The coefficients here are the biggest for C, followed by B, followed by A. So this is the best case. And because of this, what I'm going to do is that I'm going to throw everything into B. So the idea is that it's better to, instead of using general A and B, just give everything to B. So replace it by 0 and A plus B. What does it mean? Well, because if you take a look at the equation, AB plus 2AC, right? Here's something you can do. This is A times of B plus 2C, right? And then the other guy, 3BC, of course, it's just going to be B times of 3C. Now, which is bigger? Well, in the best case, C is at least B, right? So this guy is at least this guy. So that means this is bigger than this. So the idea is, basically, I just, everything from A, I donate to B, right? I reduce this down to 0. I reduce this down to the new value, which is A plus B. It will become bigger. Or at the very least, it will become the same, right? Even if it doesn't become bigger, at the very least, these two will be the same. So it's better to replace A and B by this 0 and A plus B. So once you realize that, you can realize that the best case, you can add one more condition. The best case occurs when A is 0. Right? Because A has now donated every single of its thing to B. So by doing that, you can confirm that if the best case is A equals 0, actually the single term is just 3BC. You just need to find a way to upper bound 3BC. And of course, now straight away AMGM can tell you this is at most so AMGM will tell you this is what I think it's slightly that, yeah, this is from your AMGM. You'll be able to get this. And so that's where idea one comes from. Right, you can take a look at this. Right. Yeah. So anyway, that's the final answer. So you can see idea two makes a lot more intuitive sense. Idea one is a very nice way of presenting because idea one avoids this kind of logical complication. But idea one is also a lot harder to think of intuitively. Next, we have a recurrence, but a very simple one because you can see x1 equals to 1, and if xn plus 1 is 2 times xn, then plus 1, the next number will be 2 times 1 plus 1 is a 3, the next number is 2 times 3 plus 1 is a 7, 2 times 7 plus 1 is a 15, so on and so forth. So immediately you can conclude xn is to the power n minus 1. So therefore, we want the units digit of 2027 to the power of 10. So here, to figure what this out is, I just need to figure out the exponent mod 4. I can recognize that 2 to the power 10 is 0 mod 4. So in our units digit pattern, right, when I take mod 10, what's this? Sorry, not yeah, mod 10. This is 1. Okay, so that's the answer. Okay, continuing on. Determine M where this is true. This is a very well-known question seen many times in SMO before. The solution is always the same. The idea is that 1 over square root of k can be written as 2 over 2 square root of k, which can be bounded between 2 over square root of k plus square root of k plus 1 and 2 over square root of k plus square root of k minus 1. But the fact is that we can rationalize the two of them here. This is in fact 2 square root of k plus 1 minus square root of k. This is in fact 2 square root of k minus square root of k minus 1. Okay. Now, what we have is we can continue on. Yeah. We can continue on, and then what we will get is the summation. Right? I can sum up the things on the left and on the right. Now, if you apply this even to k equals to 1, your summation actually will not be very accurate. So in fact, I'm not going to apply it to the first term, but I'm going to apply this thing here for every subsequent term from 1 over square root 2 onwards. So therefore, when I do the sum, I have m in the middle, but I know that this is bigger than 1 over square root 1, and then when k equals to 2, I can introduce this guy now, right? 2 square root 3 minus 2 square root 2, then plus 2 square root 4 minus 2 square root 3, and then plus dot until the very last term when k is 100. That's 2 square root 101 minus square root of 100. And then on the other case, basically same thing. But again, once again, I only start applying when k becomes 2. So I still keep the first term there. But then now when k equals 2, I have 2 square root 2 minus 2 square root 1. Then 2 square root 3 minus 2 square root 2, all the way until the last one, 2 square root 100 minus 2 square root 99. And so if you take a look at which terms are left over, you can see that on the left side, this guy, oh, okay, I just realized this is missing. This guy, and this guy is left over. So on the left hand side, we have a value which is 2 square root 101 minus 2 square root 2 plus 1. Now, if you calculate what this is around 1.414 times 2, so it's negative 2.8 something. And if you plus 1, if you plus this, in fact, it will be roughly 20 point something plus 1 is 21 point something minus 2.8 will give you roughly 18.3. But if you look at exactly the right hand side, it will be 19 because this is 2 square root 100 minus 2 square root 1 plus 1 over square root 1, which is 19. So m is between 18 and 19. M round down will be 18. This is the answer. Okay. Just give me 2 minutes time. I'm gonna take a charger because the laptop is running low on battery. I'll be back. Hey. Uh, Hopefully I can survive to the end of the review. Anyway, question number 10. This is a question I've seen many, many times before already. You already know the answer. You already know that basically the idea is just to pair this one with this one, and the sum will be 1. Okay? So this sum will be 1, this sum will be 1, this sum will be 1, so on and so forth. So m itself will be equals to 2025 over 2. So then 2m will round out is 2025. Now, I'll just show very simple working. I don't want to do too much for this question because I assume that 90% of people who watch this have seen this already. But the idea is that if you combine this together with the case where you have 1 minus x, it in fact equals to 1. And the idea is that, okay, I multiply by a certain thing to make sure that the two denominators are equal. And the case right here is notice that the number 3 is not random. 3 is 9 to the power half. So the thing we're going to multiply by is 9 to the power of x minus half. Yes, correct. And then now, very interestingly, the second term will become a 9 to the power of half over 9 to the power of half plus 9 to the power of x. So this is exactly 3 and 3. Right. So once you realize that, then you realize, oh, that's just the complement of this one. Right. So therefore, this sum is 1. Next, question number 11. You have this question that is like seemingly random in some sense. Right? Because what it gives you is that it gives you, some 1 or negative 1 times square number, and then you add a bunch of them together is 2026. Firstly, there should be a solution, right? Because there's so many different choices of square numbers you can use. Definitely there should be. Now, how do you find the smallest one then? Well, just try. Firstly, you must be able to at least cross the 2026 mark, right? If I choose 1, 1, 1, 1, 1, 1 all the way. So let's do some estimation. How big is adding squares up together? If you choose only up to 10 squared, then it's a bit too small. If you choose all the way up to 20 squared, it's a bit too big. Because for example, this is this value. Right, it's a bit too big. It's slightly more than 2800. So you want to go back a little bit. You can just go back by taking away 400. Okay, wait, let me write down what this is. You can go back by taking away 400 and 361, right? So if you take away 761, then you get to 2109, I think. So that's 1 squared plus 118 squared. Now, can you flip some of the ones to negative 1 to make sure that if I change, for example, plus or minus, this number can become 2026? Well, the answer is no. Not for this number here. And the reason is because 2019 is an odd number. Whenever you change a plus to a minus sign, you are decreasing by an even number. If you choose a plus to minus sign, you're decreasing by an even number. So then you should also decrease the right hand side by an even number. So this thing can never get up to, can never get down to 2026 by subtracting. Or what about the case in between? Well, that one is 2470, right? Because it's your minus 400 from here. Then that one seems to be possible. That one seems to be possible because what you just need to do is to flip what? Is to be able to flip 2470 minus 2026 over 2. If you can flip 444 over 2, which is 222, into the negatives, then you can get the correct answer. So is there any sum of squares here that add up to 222? So this is the part where you do a lot of guess and check. You can do listing, you can do whatever. There's more than one answer. But the simplest one probably is 2 equals to 196 plus 20. Wait, I forgot the numbers. 25 and 1, I think. Yeah. Yeah, this works. Right, 196 plus 26 is 222. So it's possible. So just by changing minus 1 squared, minus 5 squared, and then minus away 14 squared, you can get to 2026. So therefore, the smallest one is 19. Okay, question number 12. For question number 12 here, the idea basically jumped out to me the moment I look at the question. That's because I have a lot of experience with this kind of things for inequalities. But if you don't have a lot of experience for this kind of thing, it can be pretty hard to see what to do with these terms. Now, one thing I noticed almost straight away is that, okay, this term over this term tells you that the plus one missing, plus one missing, plus one missing, those terms will add up to something as well. So immediately we can get from here 1 over x squared plus 1, 1 over y squared plus 1, and 1 over z squared plus 1. Right, the sum is 1. And once you have this expression and this expression right here, we are basically done because x squared and 1, the geometric mean is x. Y squared and 1, the geometric mean is y. Z squared and 1, the geometric mean is z. So this is an application of the famous Cauchy-Schwarz inequality. So just to recall what this inequality is, it says that a1 squared plus a2 squared plus 1 to an squared times b1 squared, b2 squared, all down to bn squared is at least a1 b1 plus a2 b2 plus all down to an bn squared. And the way to remember this Cauchy-Schwarz inequality is in fact very easy. The way I remember it is that I just remember, oh, this term is actually the geometric average of these two, right? If you multiply these two together and then you take the geometrical mean, is this guy. This one, the geometrical mean is this one. And finally, these two, the geometrical mean is this guy. Oh, like that. Okay. So here, immediately by applying this, we can see that our x squared over x plus 1 times our 1 over x plus 1, by using the inequality, what would this term be? It is the geometric mean of these two, right? And the geometric mean of these two would just be x over x squared plus 1, like that. Okay, so same thing for the rest. If I have a y squared over y squared plus 1 together with a 1 over y squared plus 1, the geometrical mean is y over y squared plus 1. And same thing for the last expression. And then we're done because 2 times 1 is at least m squared. Finish. Okay, next one Question number 13. Let x and y be real numbers satisfying this equation, and let p be the minimum value of this guy. Find the value of 4p round down. So here, you can try to do something. You can try to do a Lagrange multipliers. So if you want, you can read more about it. But I don't recommend you all use this because this uses partial derivatives, which I don't think is suitable. Actually, back then there was a question which you could also have used Lagrange multipliers, which is this one over here. But again, it was not suitable because exist far simpler ideas. So what is a far simpler idea in this question? You can just use coordinates. This is a coordinate geometry question because the first one represents the equation of the unit circle. This is your x squared plus y squared equals to 1. And what does this mean? Well, if you have a certain point where the x coordinate is 1 and the y coordinate is 2, so let's say this point right here, right? X coordinate is 1, y coordinate is 2. Then y minus 2 over x minus 1 is a gradient. If you have a random point, xy, then the gradient to this one here is exactly y minus 2 over x minus 1. That's the line, gradient of this line. But here x and y are what? X and y are points on the circle, right? So x and y are points here. So that means we can think of it as there's some kind of gradient of lines connecting points on the circle to that point there. Out of all this, I want to have the minimum gradient. The minimum gradient is which one? This one will give you the minimum gradient because it has the least slope. Right? It has the smallest slope. So this one will give you the minimum gradient. So basically, I just want to figure out the gradient of this and I'm done. How? Now, if you participated in the SMO senior yesterday, you'll know this is very similar to one of those. There was this question involving the, forget already, beta and alpha and then the square root 39 and the square root 3 question, right? But you don't have to go that far. In fact, this is a lot simpler because what you can do is that you can use the right angle here and you can also use the right angle here because these are two congruent triangles. These are two congruent triangles. Well, the one here on the right hand side is a 1 and 2. So we know, in fact, this thing here must be a square root of 5. Okay. So now I know this is square root of 5. I should know that this is 1 and 2 as well, right? But the problem is I don't know exactly where this point. So here, how to determine this point? It seems like it's impossible to do so, but we can use another property. We can draw this perpendicular. So let me draw the triangle out at the side. In fact, I'm going to draw both of the triangles. This is what it looks like. 1, 2, 1, 2, square root 5. I can draw this thing here, which is actually this green line in the diagram. Now, from the result of this green line, actually we have a, how do I say this? We have a similar triangle. Hopefully you can see that this green triangle is similar to the 1 to 2 to square root 5 triangle. So basically, once I figure out that I know what this is, which is the length here, I can figure out the values. And in fact, I can figure out what this is because of the fact that this thing here satisfies what? Satisfies this thing here times square root of 5 is equals to 1 times 2. Right? So this thing here will be equals to 2 over square root of 5. 2 over square root of 5. So this length in green color will be a 4 over square root of 5. And remember that this is also a 1 to 2 to square root of 5 kind of triangle. So when you do this guy divide by square root of 5, you can get the vertical length. That's a 4 over 5. And this will be an 8 over 5. Okay, so this point exactly will be the coordinate negative 3 over 5 and 4 over 5. Right? It is negative 3 over 5 for the x coordinate because you start from x equals to 1, you go to the left hand side, 8 over 5 units. And of course, the y value is 4 over 5 because this is 4 over 5, right? So now, the gradient will be equals to basically 2 minus away 4 over 5 over the value of 1 minus negative 3 over 5. And if you calculate out, this will be 3 over 4. And that's P. So then 4P is 3. Finish. Okay. Around this point is where the questions start to get harder. But not quite yet, because question number 14 is still a relatively easy question. It's a word problem. There are n pairs of students, each with each pair consisting of a boy and a girl. At each turn, Ming chooses one boy and one girl, not necessarily in the same pair, and gives each of them a peanut. Then the same student may be chosen more than once, and after several terms, for each pair, either the boy has 21 peanuts more than the girl, or the girl has 36 peanuts more than the boy. Sounds a bit weird, right? This condition. Okay. How to understand? In fact, for one thing here, you can ask yourself, can there be two different values of boys and also two different values of girls? So let's discuss that. If there are two different values of boys, right, so peanuts for boys and two different values of peanuts for girls, that means one of these will be a B minus 21, or one of these will be a G minus like B plus 36, because the girl will be 36 more than the boy. But the same thing for the other one. So it feel weird because of the fact that if this is 21 more than this, then this has to be 36 less than this. Then the other one also has to be 21 more than this and 36 less than this. So B1 and B2 will be the same actually. So therefore, actually there's a contradiction. It's not possible to figure out that there are two separate values of boys, two separate values of peanuts for boys, and two separate values of peanuts for girls. In fact, only one of two cases must occur. Either all boys are the same. Some girls has 21 peanuts less, some girls has 36 peanuts more, or all girls have the less or have the same. Some boys have 21 peanuts less, some boys has 21 peanuts more, and some boys have 36 peanuts less. This is either or of a situation on the diagram. You cannot have boys and girls both having more than two options, or at least two options. Now, in both of these, it should be pretty obvious because of the fact that I give a total amount of peanut to be the same for the boys and girls, right? Each pair I give one boy and one girl at the same time. The total from the boys is the same as the total from the girls in both of these cases. In the first case, if the total boys is the same as the total from the girls, then you can notice that each girl here is a B plus 36, each girl here is a B minus 21. You need to balance them out somehow to get to B, right? The answer is that you can take them in the ratio of 12 to 7. Right, if you take them in the ratio of 12 to 7, then minus 21 times 12 is the same as 36 times 7. Same thing here. The ratio here will also be 12 to 7. So either way, what does this mean? Either way, this means that he must give at least, there must be either 19 girls or 19 boys. There must be either 19 girls or 19 boys. But then that means that n must be at least 19. Finish. Okay. Let's continue on. Question number 15 is where the question starts to get pretty annoying. This question, I really don't know what they were thinking when they put this question here. I don't think this is a very a very well designed question at all. I think it's just a very randomly picked question just to make people stumble and fall. Firstly, this is not a number theory question, or rather, not traditionally number theory methods. If you use traditionally number theory methods, you'll do things like mod, bounding, estimation, blah blah blah. But actually, this is factorizable straight from the beginning. How to see it's factorizable? If you set a to be negative 2b, then this is negative 8b cubed. This is 4b squared, 4b cubed, this is 4b cubed. They add up to 0. So because of that, actually there will be a factor of a plus 2b on the left. And then the rest is going to be this. I mean, that's already a very weird first step, and I don't really like it because of the fact that you have to notice it's factorizable, which is not where most people would think when you look at this. Secondly, you have to factorize 7087. You have to go and check not divisible by 235, pretty easy. Not divisible by 7. Not divisible by 11. And then you can check manually divide by 13, manually divide by 17, right? And then that's where we can see that actually, 19 is a factor. And once you do that, you need to go and look at the 373 and check again. Okay, not divisible by 19, not divisible by... Actually, you only need to check 19, right? Since you know it's not divisible by 19, you know it's also not divisible by 2, 3, 5, or 17. So you know that it's a prime. But anyway, that means that if you take a look at this expression, there should only be two possibilities. Now, which are the two possibilities? 19 times 373 and 1 times 7087. Why cannot be negative? Because this guy cannot be negative, right? This guy, if you complete the square, quite easy to see, cannot be negative. Why cannot be 373 here and 19 here, for example? Again, if you compare the values, if this is 373, there's no way that this is going to be 19, right? It's going to be a lot bigger than that. So then these are the only two possibilities. Now, that's where you go and solve each of them manually. And this is pretty tedious as well. Because what you need to do for the first one is you check. Okay, by the way, you want to start with the first one because it feels a lot more natural, right? You check the first one by doing a plus 2b equals to 19. So a equals to 19 minus 2b. And you put inside here to solve a quadratic equation. And then you can figure out the answer. So it's not nice. Turns out there is a solution here, b equals to 12. And so that means that a will be 19 minus 24, negative 5. Okay. So I don't like this question. You can see it's very not nice. A squared plus b squared is 169 in the end. I also don't like question number 16. Question number 16 is a geometry question, or at least it seems that way. Until if you try to solve it synthetically, that means using traditional geometry ideas, angle chasing, length ratios, blah 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 blah, then you realize that, hey, wait a minute, there's no nice way to do this question. The only way, as far as I know, to do this is to use coordinates because of the very weird formulation of this question. Okay? Let's take a look. So what this says is this. You have a circle, omega, a big omega outside actually, then there's a circle small omega inside. Then they tell you that the radius of the two circles are 18 and 54. So if you try to draw them out, let's say the big circle is centered here, this will be 54. Small circle with a radius of 18. So therefore, if you actually go and calculate out the various lengths, you can figure out that. Let me zoom in a little. What is the question? Okay, let me zoom in a bit. You can actually figure out that certain lengths you can figure out. This is 18, 18, and then 6. Then this is 12. Okay, so you can figure out these things about the diagram. And then continuing on, what they're saying is this. You have O, right, I, and then we have a AB is a chord, which is tangent to the circle. For example, somewhere like here, right, tangent. And then now, C is the circumcenter of IAB. So if you draw the triangle IAB, we're going to find the circumcenter. So that means pretend that there's a circle, you can draw through these 3 points. We're going to figure out where the center is going to be. So according to this diagram, it should be somewhere here, right? Maybe it's inside the circle, maybe it's outside the circle, we don't really know. Now, another way to draw your circumcenters is you don't need to draw them. You just need to know they are the perpendicular bisectors of the 3 sides. It must be a perpendicular bisector of AI, perpendicular bisector of IB, and perpendicular bisector of AB. So in that case, probably you see it meets somewhere outside, right? So C probably somewhere outside is a very natural point. And then as a result, because it's the circumradius, actually AC, IC, and BC are the same. And so these are all results from geometry. But it is at this point that the geometry part of the question ends. Okay, maybe there's still one more. Let me draw one more thing. There's still one more result from geometry, which is that because it's the perpendicular bisector of AB, it will pass through O as well. Okay, so OC is a straight line, perpendicular. Okay, so this is what the diagram looks like. Now, as explained previously, we're going to set coordinates. Firstly, let's make the diagram bigger so that you can see everything. Actually, no, I'm gonna refrain from doing that first. I'm gonna suggest some ideas first. One idea that you might have, at least the idea I had at the start, was to set the origin as the center of the circle, big circle, O. And this is a very natural idea. Right? Set the center as set the origin as the center. Wait, no, set the center as the origin. Because now you know that, for example, this point, they satisfy x squared plus y squared equals to 54 squared. Right? But the problem with that is because of the fact that this is slanted, this is slanted, this is slanted. It's very hard to figure out anything regarding this. And in fact, OC is slanted as well. So once you do it that way, it's not very nice. Even though these coordinates are nice, the rest of them are not very nice. So what we can do here is that we can do a slight change in the diagram. We can do coordinates. But with this as our x-axis and with this as our y-axis. This makes a lot more sense now because I already know that this is going to be horizontal, this is going to be vertical, this is going to be vertical, right? And now I'll choose my origin. Again, you can choose this as your origin, no problem. But maybe it makes a lot more sense to choose this one as your origin now. Because of the fact that it is just nice at like some kind of center-ish position, right? Okay. So let's do that. So I'll set this point, which I don't have a name for it, by the way. So let's start naming the points. So the point on the right, I'll call it D, and this point here, I'll call it maybe M. Okay. So what we can see here is that let M equals 0, 0. Okay. Then what we can do over here is that we can set a bunch of equations. Right. If M is 0, 0, let's set these two things. Let A be negative x, right, why not? Negative x, 0, b equals to x, 0. Let O be equals to 0, y. This one right here. Immediately we have something, because OA is the radius, and the radius is actually 54. We immediately get x squared plus y squared equals to 54 squared. Next, we have some suspicious amount of length we are moving towards the right side. And then we move some suspicious amount of length upwards. In fact, we know this what this length upwards is. Okay, it's not suspicious, it's in fact 18 because that's the radius of the circle. So we move, let's say, amount to the right. I don't know, let's call it D, right? For I don't know, just some random letter. So then we can let D be equals to D, and then you go upwards by 18. So this is the result. Now, what we also have is that this is the point. Sorry. D is D0. I is D18, right? Because of the fact that I go up by 18. Now is the point where you can use this fact that OI is equals to 24. So then, this to this is 24. In other words, D squared plus Y minus 18 squared is 24 squared. Okay. Now, what do I want to find? I want to find a certain point here that satisfies the property that the distance to these three are equal, right? And in fact, these two is the same. So we can just focus, for example, on here and on here. So final thing we're going to let is we're going to let C be equals to maybe just, okay, firstly it's going to be 0 for the x coordinate again. But then for the y coordinate, let's choose, maybe let's just choose C because it's at C, right? And then we can set them up like this. So CI equals to CB, right? So CI is, you go D units, right? You go this, this is C units here and 18. But actually, if you combine the entire length, it's 18 minus C, right? Because this part here is technically negative, right? So it's 18 minus C. That sounds correct. So it's D squared plus 18 minus C squared. And then we take the square root. Right? Okay, so let's just write it as CI squared, for example. And then what else do I have? We also have something else. CI squared is also equals to this guy, CB squared. CB squared is equals to C squared plus X squared. Okay. Oof, it's a pretty big mouthful, right? Okay, finally, what do I want to find? I want to find the value of OC. OC is in fact the distance from here to here. So in fact, OC, if you look, this is y coordinate, C, this is y coordinate y. So in fact, the value is just y minus c. Is it possible to figure out straight away what this is? Well, we have to find some way to combine them, isn't it? So yeah, I'm gonna write this thing here. Replace this guy inside here. I'm gonna replace this guy inside here. So what I can have is d squared is 24 squared minus this. So 24 squared minus away this guy plus this guy is c squared plus x squared, which is 54 squared minus y squared. Absolutely disgusting, right? If you take a look at the working here on both sides. But very nicely, actually, you can find y minus c because of the fact that if you expand out, okay, let me see what I can do here. So if I expand out, I can firstly throw the 24 squared over, like that. And then what I can do is that on the left hand side, when I expand this 18 squared and this 18 squared, they'll cancel each other out because of the subtraction. You have a minus y squared, you have a plus 36y, you have a minus 36c, you have a plus c squared. Okay, so this is gone, this is gone, this is gone, this is gone. And then so y minus c is in fact 54 squared minus 24 squared over 36. Oof, that was a mouthful. But anyway, we are finally at the last step. So here we can apply difference of squares. 30 times 78 over 36, you can see it's just 5 times 13, 65. Okay, now let me mention my remark on this question. I absolutely dislike it. I think this question is very painful. I'm not quite sure again what's the purpose of including this question on SMO. Question 17. I love this question 17. Sudden change of tones, isn't it? Just now I just mentioning how I hate question 16, but now I say I love this question 17. This is a very fun question to me. You have a kind of feeling like somewhere in between the round 1 to round 2 type of functional equation. F of x plus y is equals to fx times fy minus 4 sine x times sine y. Firstly, what are your guesses? Well, the function f should be some kind of trigonometric function, right? And that makes sense because the function f has some kind of maximum. So probably it's going to be periodic, right? If it's some kind of trigonometric function, maybe like sine or something like that, periodic, so definitely should have maximum. Okay, let's solve. So when you do functional equations, one of the standard industry techniques, so what we call industry techniques is people always do this to make it convenient, is to set this statement as pxy. And then now you can just put x and y as random values to see what happens. For example, if I want to find f0, which is one of the most basic things in functional equations, I can just put p00. Okay, actually this is useless because I'm going to show you why p00 is useless. If I do p00, the equation it gives us is f of 0 equals to f of 0 squared minus 4 sine of 0 squared, which is 0. Why is this not very useful? Well, because f0 can be 0 or 1. Actually, there's another thing you can do to straight away tell the value of s0, which is not to substitute both values, but only to substitute y equals to 0. If you only substitute y equals to 0, then the equation becomes fx equals to fx f0, and then this is sine 0, which is 0. And this statement is true for every value of x. If this statement is true for every value of x, then immediately you can see that f0 will be 1. There's no other possible choice, right? Actually, there is another possible choice. The other possible choice is that fx equals to 0 for all values of x. But of course, if fx equals to 0 for all values of x, it doesn't work. Then now, how to continue? Well, you need to try to use f0. So one thing you can try to do is that maybe you create 0 here. So you can set px negative x. So here we replace all instance of y by negative x. So I have f0 equals to fx, f of negative x, minus, actually it's plus 4 sine squared of x. Because sine of negative x is the same as negative of sine of x. And this is 1. Now this actually will become very important later on. You'll see why. To see how to use these equations, and if you try to put in most other things, they will become kind of useless. Yeah. To see how to use these equations, the trick is to realize that, okay, if I can somehow make a lot on the right side disappear, it will be nice. How to make a lot on the right side disappear? If, hypothetically, there was f of something that gives you 0, let's say f of something gives you 0 here, then I can put the value a inside here. Boom, this entire thing disappears. So you get sine of a times something. So then it's a very nice looking expression on the right hand side. The question becomes, can we get some kind of value such that f of a equals to 0? Turns out the answer is yes. And the way you get it is to look at this. Inside this equation, here's what we're going to do. We're going to let x be equals to, or rather, we let sine of x equals to half. If we let sine of x equals to half, this is exactly 1. But this is also 1. So the result is that fx times f of minus x equals to 0. Then we figure out that there's a value of f which will give you 0. Now what's the value of x though? It's the value of sine that will give you half, right? So the value of x is basically going to be exactly, what's this? 30 degrees, which will be pi over 6. So as a result, we know that either f pi over 6 equals to 0 or f of negative pi over 6 equals to 0. But it doesn't matter because we have achieved our objective. Our objective is to get f of something equals to 0, right? Okay. So it actually doesn't matter which one we use. Now, so we say that, okay, we can let f of a equals to 0. So a, I can choose either this guy or this guy depending on what the question wants us. And now, let me carry out my idea just now. I'm going to put p of, let's say, x and then a. So I put y as a now. It tells us f of x plus a. And with y as a, boom, this disappears. You just get minus 4 sine x sine a. Now, what do you notice? This is a statement that's true for every value of x. And you are basically done at this point. How come? The final step you just need to do is to replace x plus a by x. How to replace x plus a by x? One way to do so is to say, maybe I let y be equals to x plus a. Then this is saying f of y equals to, if y equals to x plus a, then x is y minus a. So it's minus 4 sine y minus a sine a. Done. We have solved the functional equation. This is exactly how your function fy should look like. Now, let's bring it back. The value of a here, there's two different values, right? Pi over 6 and negative pi over 6. So sine of this could be sine of pi over 6 or sine of negative pi over 6. You don't know. So because of that issue, we can put a plus minus in front. Right? But here also two values, right? So let's throw away, let's say the negative value. Let's focus on the positive value for now. Let's say that a is equals to pi over 6. Then how? If a is equals to pi over 6, then sine of pi over 6 is equals to half, right? It's just negative 2 sine of y minus pi over 6. And in fact, from here, you already know the answer. If it's negative 2 times of the sine of a function, the largest possible value of this function as y changes among every single answer should be 2. So that's the answer. Now, if, however, you are doing this as a round 2 type of question, you are still not quite done yet. You need to do something else. You need to check that this satisfies the original functional equations, right? Okay. So this part is not necessary, but if you are a round 2 kind of person, then you need to know this part. How to check it satisfies the original one? We can substitute this in. But before I substitute in fact, you can simplify what this function looks like. We can simplify this function because I can use sum of angles for sine to simplify this, which is let me write somewhere on the left. Minus 2 sine y cosine of pi over 6, right? Minus 2 sine of negative pi over 6 cosine y. So this is going to be negative square root 3 sine y and then cosine y, right? Okay, so you take this one, you substitute back into the original equation, check whether it's true. So let's do a quick check. I'll do the check at the top of the screen here. So check. To check that this is true, what we do is that we just take our previously gotten value, f of y equals to negative 3 sine y plus cosine y, put it into the two expressions. Oh, I really don't want to do this. Okay, never mind. I'll leave it as an exercise for you then. You can check that this is true just by substituting it in. Okay, I trust that you can work it out yourself and feel it and verify that it's true. So anyway, yeah, so that's why our function here works. Okay, so that's why I kind of like this question. In fact, the reason I like this question is because of this step here in purple color. Using the fact that f of something equals to 0 to help us kill this term over here, make it disappear. Okay, now we immediately jump from a question which I like a lot to a question which I don't like a lot. Again, one might ask, what's the purpose of this question number 18? Okay, but this question number 18 is very guessable, I feel. At least the boundaries of your square root x1 plus square root x2. The reason is because, okay, actually there's two groups of possible equality cases here. When you take a look at this question, you should realize that I don't need to use all 2026 variables, right? If the answer is nice, at least there shouldn't be a need to use all 2026 variables because this is SMO, right? Open round one. So a lot of them are going to be straight away just 0. So then my idea was that, okay, if I have a bunch of zeros at the end, maybe the equality case is when they're equal. So maybe I have x1, x2, all the way until some number is the same. And all these numbers are the same as well. In that case, n times of x1, maybe I can choose it to be around 400. And then maybe I have n times of x1 squared to be 10,000. And if I compare them, x1 is just 25. So immediately one equality case is, you can see simply just 25, 25, 25, 25, 25, all the way until x16. Why x16 is because of the fact that there is 400 as a sum. And then just 0 all the way. Okay, you can check that this is exactly 400 here. You can check that this is exactly 16 times of 625, exactly 10,000. So in this case, you can see that this is equals to 10. Now I have to admit something though. I didn't manage to find the other equality case until someone else pointed it out for me. There is another equality case in this question. You could also achieve equality by doing something even simpler. Just choose x1 as 100. Because you don't need to satisfy this, right? If you just choose x1 as 100 and the rest of them as 0, automatically this also works. So then square root of x1 plus square root of x2 is just 10 plus 0. It's still 10. So there are two separate equality cases. How do you work with a question with two separate equality cases? It's usually quite challenging. But here's the idea behind this question. You want something that is strictly can be used for both cases at the same time. And the idea is that we're going to use this when I is at least 2, when I is at least 2, xi squared is less than or equals to x2 times xi. Now this is obvious, right, from this given condition, because xi is less than x2, that's why xi squared is less than or equals to x2 times xi. But you notice something, this inequality is used both here and here. In the first case, if they are both 25, obviously this is true. But if they are both 25 and 0, then this is also exactly true because 0 squared is less than or equals to 25 times 0. So it's also a tight inequality. And of course, in the second case below here, 0 squared is less than or equals to 0 times 0 is also true. So this here is a tight inequality you can use for either case 1 or case 2. This is the strongest thing you can use. And now notice something else. This one here, we don't actually need to satisfy. However, this one here is tight exactly at 10,000 for both of our equality cases. So we do need to use this quite important fact. Okay, so how? Well, let's use this thing over here. So that means my x1 squared plus x2 squared plus all the x 2026 squared, I'm going to replace it by x1 squared plus x2 squared, or rather x2 times everything else. Okay? So that's the trick. I'm going to replace this terms behind by this thing. But then now, because of this condition here, right? Oh wait, sorry, I forgot something. I forgot x2 times x2. Right, I got the x2 times x3 inside, but I forgot the x2 times x2. And then this guy here, I can now replace by what? Something that is at most 400 minus x1, right? So now I know something, right? I know that this is at least going to be 10,000. So we have directly some condition with this 10,000 behind. But again, there's still two equality cases, right? So how do you figure out that this will not have anything smaller, for example? You can ask this question. What happens if x1, if the square root of x1 plus the square root of x2 is less than 10? Okay, so what we can do is this. We can let variable a be equals to the square root of x1. We can let the variable b be the square root of x2. Okay. I want to discuss what happens if a plus b is less than 10. Then, firstly, this guy is what? This guy is going to be a squared, so that's a to the power 4. B squared, 400 minus a squared. Okay. And the fact is that this thing here will be strictly less than 10,000 if a plus b is less than 10. How come? So you know that something is true. Okay? You know that a plus b is less than 10, right? So in fact, this thing here can be rewritten. And this is the part I don't like about this question, because I think this is extremely tedious. This is the part that can be written as sorry. Let me use the fact that if a plus b less than 10, then one important thing is b less than 10 minus a. So if I use it over here, it looks like this. Wait. No, wait. Sorry. No. I want to keep the 400 minus a squared. I want to keep the 400 minus a squared, and I want to replace b with this guy, b less than this, right? So like that. And then by simplifying the expression, actually you can get the number 10,000 appearing. Now you might be wondering, how does 10,000 appear? Because this is a very convoluted thing. I didn't manage to find this because the calculation was too tedious. But it's actually 10,000 minus away something else. Okay. So then you must be very happy that 10,000 minus something, yes, you have shown it's less than 10,000. But no. See this a minus 5 here? This thing here is only true if a is larger than 5, right? So actually we need to do another specific subcase about if a is less than 5, what happens? Right? If a is less than 5, we need to do another specific subcase. If a less than 5, then we do this another way. We do this by saying that, okay, if a less than 5, then this is no longer useful. Because if a less than 5, b cannot be, for example, like 6, right? Right? If a is 4, b cannot be 6. Because of the fact that b is naturally less than a. So if a less than 5, the thing that we're going to use here is in fact b less than a. So this thing here is going to be like that. But then 400a squared, if a less than 5, is definitely less than 10,000 as well. So then we are done. We have shown that in fact it's not possible. It's not possible for this to be true. Whether it's in case A or case B, both of them will be less than 10,000. So therefore, the minimum value is 10. Finish. Right, and hopefully you can see why I dislike this question so much, because of the fact that I don't think these are very motivatable. Okay, I think the one at the bottom, not too bad. Right, but the one here, no one is realistically going to be able to see this. Right. Okay. Yeah, so that's the question. Question number 19. Okay, this is a question that is quite approachable. By approachable means that even people who are Sec 1 or Sec 2 this year, they can already start to attempt questions like this. You want the largest n so that there exists a and b such that this is always true for all x between -1 and 1. Now, I've done such a question like this before, but I forgot where. That's the problem. Oh, okay. Last time in the SMO Senior 2013, question 34, I don't know, maybe I might be wrong. There was a question that says something like, okay, if ax squared plus bx plus c is less than equals 1 for all x between 0 and 1, then take a look at the value of 2ax plus b is less than equals m. And turns out the answer for this is m is at most 4. So it's a very similar idea to this question. The intuition you must get is from graphing. Okay. So the intuition for this question comes from graphing. How does graphing give you any intuition to do this question? As because of the fact that the 2026 plus x squared is very easy to draw. From -1 to 1, it just looks like this. This is also pretty easy to draw from -1 to 1, except that you have an absolute value outside. But you can still understand this pretty easily inside. Inside, I have x squared, which is obviously this. I have ax. Now here, because I don't really care, because of the rest of the them being symmetric, I can just assume, for example, a is bigger than 0. And then b is just a vertical shift of the graph. Right? Whether I shift the graph up, whether I shift the graph down. What happens if I add these two? The idea is that, if I add these two, the part on the right side is still going to go up, increasing, right? This is an increasing part. You add the increasing part, it's increasing. So then your b should do a job to pull it downwards, basically. So when you add x squared plus ax plus b, I'm going to ignore the right hand side first. I'm going to just draw, the left hand side. I'm just going to draw the right hand side. The effect of b should be to pull the graph down. Why you want to pull the graph down? You want to pull the graph down because of the fact that when you take the absolute value, you want to have a certain kind of reflection. Like that. And by pulling the graph down, you can have a shorter reflection. Right? If you put the graph down exactly halfway, where these two things are equal in height, you can shorten the height by half by taking this b here. And now if you shorten the height by half, then let's say this part is fitting something that's really, really small, a small range of values. Then when you multiply by n can become a very large number. So that's the idea. And once you can understand this, you can understand why in the ideal case, a is supposed to be 0. Because a, you notice what it does is just it needlessly increases the value of x squared on the right hand side. Right? Initially, x squared is already like this. If you add ax, it's going to go even higher, isn't it? Right? If this is the graph of y equals x squared, then the graph of y equals to x squared plus ax will look like this, maybe. Something like that, right? Even higher, which means that when you do this bounding, it's not as nice. So in the ideal case, actually a is supposed to be equal to 0. What about b? In the ideal case, a is supposed to be 0, and then b is supposed to be, you might think it's half. You might think it's half, or rather negative half. Because if you have b to be negative half, you put it down exactly halfway. This is negative half, this is half. You reflect negative half and half, right? Just nice, you can do like, how much? You can do a multiple of 4052 times. You can reach this level. But turns out there's a slightly better number to choose. These two things, the gap, the difference between them is always 1 in terms of vertical height, right? Because it's y equals to x squared, you just put it downwards. So when you reflect back up, these two values of y will add up to 1, right? Because of the fact that these two difference of y is 1. And these two values of y add up to 1. When I multiply by 2026, when I multiply by n, ideally this point now will reach this point. Ideally, this point here will reach this point. So ideally, you have a value here at 2026, you have a value here at 2027. So then 2026 plus 2027 is 4053. So in ideal case, if this was 2026 over 4053, in ideal case, if this was 2027 over 4053, then when I multiply that, I can get here. So in the ideal case, basically I choose B to be negative 2026 over 4053. I should get that to work. N will be equals to 4053. Now, all these are done by intuition. All these are done by intuition. And each of the steps I mentioned are not too hard to derive yourself intuitively. However, some people may prefer a more algebraic solution. In that case, I also provide another one. If you're looking for an algebraic solution, then here's the idea. The idea is that we just put the x values inside. X equals to 0. N times this is at most 2026. X equals to 1. N times this is at most 2027. X equals to negative 1. N times this is at most 2027. Okay. So now what we can do is that we can attempt to combine them together. Or at the very least, we can try to combine these together. These things give 2 plus 2b, and then now you can compare with this, right? So 1 plus a plus b plus 1 minus a plus b is equals to 2 plus 2b. Okay. So then we substitute the values inside. So b use 2026 over n. Okay, here we can take absolute value, but we don't really care. It's a small detail. It's not that important. This is 2027 over n, 2027 over n, something like that. Okay. And then, so therefore, you can figure out the best case of n, right? Once you go and solve this thing is, wait, I feel like I made some mistake somewhere. Wait, the best value of n. Did I make a mistake anyway? Wait, I feel that I have. Wait, just give me a while. I'm trying to see what mistakes I made. Oh, okay, I cannot do this because the inequality is the same direction for all of them. Okay, I realize my mistake now. Then let me fix it by doing... Okay, never mind. I still need the absolute value. So here's what I'm going to do. Sorry about that. Here's what I'm going to do. I'm going to combine them by saying, okay, firstly, 1 plus a plus b, 1 minus a plus b, minus 2b. This is 2, right? But now, I will take absolute value. Okay, I'll take absolute value. And when we take absolute value, when you have absolute value of x plus y plus z, this is less than or equals to absolute value x plus absolute value y plus absolute value z, right? So 2 is less than or equals to this guy plus this guy plus 2 times of this guy. I'm converting the minus into a plus. So that's where we can get all the inequalities on the same side. So this one here will be less than or equals to this one 2027 over n, 2000 over 2027 over n, 2026 times 2, right, over n. And if you add them up, now I think it's correct. Yeah, because you get 4053 times 2 on top. So therefore, n from here is at most 4053. And then now the construction just proceed as how we did for our intuition part. Okay, question number 20. I'm happy. I'm happy there's at least a normal question within the rest. And I'm happy that there's a question here which at least if someone who is secondary 1 or secondary 2 come here and do, they can at least do or at least attempt it. In a circle with, sorry, in a triangle with the circumcircle being omega, you have a 12, 9, and a 90 degree. So it's a 15, 12, 9 kind of triangle, right? But you don't really need to know the 15. Because the next step, they want you to draw the tangent at this point C. And you want to draw a tangent at this point C in a way such that it extends to cut AB extended at some point, which is D. Then let E be the midpoint of CD. And then the point F is when you extend EB and then you hit a line AF parallel to CD. Find the area of the triangle ABF. Now, here's the idea. When you have similar triangles, it helps a lot to find the area. In fact, I went through this idea together with our, which class was it? My Sec 2 advanced class, the one on Sunday afternoons. And then this was part of the AMC 12 paper, the question 24 of that particular AMC. Yeah. There was a question, the practice paper 1 we did back then. Right? If any of you remember that, if any of you are watching. So that one is pretty similar. The idea is that to calculate the area of this one, we don't calculate the area of this one. We instead calculate the area of this one, and then we use similar triangles. Right? They are parallel, so we can do that. So in fact, the area of ABF is how much? Well, I have to know what the ratio here is, right? And here's where we need to know another fact. When you have a circle and any triangle, doesn't have to be right angle, when you draw the tangent at the top, you will get similar triangles because this angle here is this angle. So what we have is, in fact, in this diagram, we have triangle BCD is similar to triangle CAD. So BCD is similar to CAD. Okay, BCD is similar to CAD. And in fact, we know the ratio of similarity very easily because of the 9 to 12 on the shortest length. Right? And in fact, you know the ratio is 3 to 4. So what does that mean? That means the other ratio is also 3 to 4. BD to the other triangles CD is 3 to 4. CD to the other triangles AD is also 3 to 4. So BD to CD is 3 to 4, but CD to AD is also 3 to 4. So in fact, this is 9 to 12 to 16. This is 9 to 12 to get 3 to 4. But then the other one is 12 to 16 to also get 3 to 4. That's why actually it is 7 to 9 over here. So the area of triangle ABF is going to be 7 squared over 9 squared of EBD. And EBD is in fact going to be half of CBD, right? Because of the fact that E is the midpoint. So 7 squared over 9 squared times half. And now I need to find this area. How? We don't. We can use the original triangle's area, and you can see that, oh, these two triangles, the ratio is 7 to 9 because the bottom part is 7 to 9. So this area here will just be will be 9 over 7 times of this area, which is what? Which is the area of the original triangle ABC. And the area of the original triangle ABC is equals to half times 9 times 12, 54. Finish. Okay, we have not that many questions left. 5 of them. I'm having a kind of like a stomach pain for some reason. Not too sure why. But anyway, question number 21 is a free question because you all should be able to guess this answer very easily. It's extremely guessable. It's just going to be A equals to 2, B equals to 1. Again, because the answer is so guessable, I don't really know why they put this question right here. Because anyone who solve this thing, they will not really be using the correct method for this question. Although the correct method is not difficult. What's the correct method? Cauchy-Schwarz inequality. I multiply this by A plus 2024, and then I have a B plus 2025. The geometric mean of these two is 2026. The geometric mean of these two is 2026. Okay, so this is 3 plus 2025, 2024 plus 2025. This is in fact 2 times of 2026 times question mark is at least 2026 squared. So then the question mark is, wait, why did I do wrong? Oh, sorry, I forgot the square root on the right hand side. Square root, and in fact this means that this is wrong, right? Because this is the geometric mean for these two. So then the right hand side when you square it, I think it's 4 times the 2026, right? So question mark must be 2. Finish. This is by using the Cauchy-Schwarz inequality, right? One line solution basically. Okay, question number 22. This question, I absolutely detest this question because I had to go and Google what exactly was this fact we can use about quadrilaterals. In fact, up to today, I've never heard of this fact before. Okay, I've heard of something with that name before, but I never knew it was possible to be able to calculate in this way. So let me see if I can still find the name. Just give me a moment. I lost it somewhere inside my workings. Okay, this is the Brett Schneider's, clearly a German name, Brett Schneider's theorem. Okay. So some people apparently also call it the cosine Ptolemy, whatever that means. Okay, so what this thing says is that in a quadrilateral, doesn't have to be anything, any special shape, just A, B, C, D, and then E and F to represent the diagonals. We have this equality. E squared F squared equals to AC squared plus BD squared minus 2ABCD, and then cosine of, let me see, which angle? It doesn't matter because cosine of this plus this and cosine of this plus this is the same thing. Right? So just cosine of one of them, doesn't matter. Let's call it A plus C. This is what it looks like. The Brett Snyder's formula, aka cosine Ptolemy. I've never seen this thing before in my entire life, so of course none of you are expected to know it, but I've tried to use any other methods to do this question. I failed to do them, so I think this is the only way, which is a little bit of a not very interesting question because I just plug in the values, and when I plug in the values, the other diagonal I think is 13. One thing here is, wait, which is opposite? 14 and 21 are opposite, right? Yeah. And then the other two values, AB squared, CD squared, minus 2, 14, 21, AB times CD. And then here cosine of 90 degrees is 0. So from here, you can figure out that AB squared CD squared is in fact, just take this minus this, it's going to be a nice answer. Turns out it's exactly 900. So then, answer is 30. Okay, a total waste of time. I don't know why I even go through this question. Okay, next one, question 23. This is again a very common question in the SMO. The idea is that x is simply just square root of 1 plus x. Now, there is a particular worksheet we have done this before actually in our, I cannot remember again which class it was. Cannot remember. Yeah, but we've done this before. The idea is the same as what we did last time in, I think, either our Sec 2 Sem 1 class or our Sec 3 Sem 1 class. Forget already. The idea to have this is very simple, right? It just basically, you can replace x by itself. So you can continue forever. You can continue forever. And if you continue forever, then basically this part here is the same as x itself. Now, to prove that this is the only case, you can discuss. If x is bigger than this guy, you can see that x will be bigger than this guy. And then this pattern will continue on. X will be bigger than the next guy, x will be bigger than the next guy, and so on and so forth. Same thing here. If x is less than this guy, in fact, you can conclude that x will be less than the next guy, x will be less than the next guy, so on and so forth. So that's why the only solution is this one. So then x is obviously the golden ratio. It cannot be the negative value because this is positive. So if x is the golden ratio, actually you don't need the golden ratio. You can just use the fact that x squared minus x equals to 1. And then this guy here becomes x squared minus x, right? And then the in front part becomes x squared. And then you bring down the minus x plus 1. So this is just 2. Finish. Okay. Question number 24. Let a squared plus b squared plus c squared is 4. Find the maximum value of this guy. Well, first, let's just assume a, b, c are all bigger than 0. Because there's no reason not to choose positive values. And then what happens is that you should feel that maybe it makes sense for a and b to be equal. And in fact, that's the correct feeling. The idea is once again our smoothing argument we presented before. If you replace a and b by a plus b over 2 and a plus b over 2, the value will become bigger here. Right? Because if you have a fixed sum, the product is the biggest when the two numbers are closest to each other. And in fact, you even make c bigger as well. Because if you replace a and b by this thing here, this value will decrease. So then c squared will increase. And if c squared increases, then c will increase. So by doing this replacement, you will ultimately increase the value of this product. So in the ideal case, you should see that definitely a is equals to b. So then now you have 2a squared plus c squared equals to 4. And I want to maximize 4a squared times c plus half. At first, when I was looking at this, I was thinking, okay, probably some form of AMGM. But because of the half, it's a little bit awkward. Of course, you can separate it out to 4a squared c plus 2a squared. And then you can try to apply AMGM over here. But it just doesn't look nice. It just doesn't look nice. There's no nice way to apply AMGM. So turns out one of the better methods you can do instead of applying AMGM is to do what most people in schools do when they try to find the maximum of a function. Differentiate it. This is in fact going to be what? This is in fact going to be firstly is 2 times of this guy. So it's 8 minus 2c squared, c plus half. So if you take a random 8 minus 2x, sorry, 8 minus 2x squared, x plus half, and differentiate it, right, you can figure out where this is the equals to 0. So just expand minus 2x cubed minus x squared plus ax plus 4 d dx gives minus 6x squared minus 2x plus 8. And this is in fact factorizable. This is factorizable because you have x equals to 1 as a solution, right? And x equals to... Oh, okay, actually you can divide by 2. I didn't even realize, right? You can divide by 2, get this first, and then the other one will be, I think, 3x minus 4. Something like that. Wait, no, something feels wrong. I think it's 3x plus 4. Yeah. Okay, anyway, the best scenario is what? X equals 1. So over here, the maximum is when c equals to 1. So then we have the answer. The answer will just be equals to 6 times 3 over 2, 9. And finally, we are at the last question. Now, I like this last question. Although I will mention something. I'll mention something that I didn't mention to do this. Someone else gave me the idea. But I like this last question because of the fact that it uses an idea we have seen before. It's just that something that's not very, how do I say, not very common. Not very common. So what's the idea here? If you recall, we can refer to some previous questions which look like this. In particular, in the SMO Junior, you should have seen before many of those questions which have something that looks like this. 7 plus 4 squared, 3 square root, 7 minus 4 squared, 3 square root, and then add them together, right? And then what's the way you do that? The way you do this question is that, okay, I set this as x, I square x, right? I do a plus b, blah, 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 right? Same thing here. Although each of them individually, they are hard to deal with, but we can do something with them, squaring after add them up. Right? We are going to add up the numerator together with the denominator and then square. But there are so many terms. How to square so many terms at the same time? Well, we don't. We look for those with the same numbers inside and then square them. So we are looking at this guy and this guy, and then we will square them together. So what happens if you square such a term? Well, if you square such a term, you can get a squared b squared plus 2ab. And the 2ab term turns out to be this times this, right? Which is 10,000 minus n. Okay. Now let me mention something. If I take out the 2 here, you should notice that this looks suspiciously familiar. This looks suspiciously familiar because this is, in fact, how these terms look like from n equals to 1 to n equals to 999. It's just in the reverse order. So when I take the square root on both sides of this thing, we have this guy plus this guy is equals to, right, the square root of that, square root 2 times this guy. And now over here, I'm going to sum the entire thing. I'm going to sum n equals to 1 to n equals to 9999. When I do the sum, what happens to the sum of all this? It is the numerator. Right? It's exactly numerator when I sum from n equals to 1 to n equals 9999. Oh, okay, wait, the screen is a bit too low, you cannot see it. This one right here. When I sum this one from n equals to 1 to n equals 999, you get exactly the denominator. And then finally, when you sum the right hand side, you just get what? Square root 2 of the numerator. Because of the fact that it's just the reverse order, right? And then we're done. So from here, you can see that let's use simplified variables. N plus d is square root 2 of n. So then d is equals to square root 2 minus 1 of n. So then n over d is equals to 1 over square root 2 minus 1, which is square root 2 plus 1. And so this is the value of w. And finally, they want w squared minus 2w. Using the value of this, we can figure out answer is 1. Okay, and that is the SMO paper. I feel that there's a lot of weird questions in this paper. So many weird questions. See, there's very few truly in the spirit of Math Olympiad, but I guess it is what it is if they want to make it a lot more school syllabus based or something. Anyway, that's all for today. Go and rest well, right? Enjoy your holidays or your holiday classes, whichever one you're on right now. And now I'll go and poop. Bye bye.